Hello, my good friends. My name is Teteje Kepsi Richard. Welcome to my online class. Today, our discussion on numerical and computational method will still be on finding root of complex polynomial functions. So remember, the fundamental theories of algebra says that when we meet a complex polynomial function, at least one real root exists, or at least that polynomial function have one real root. And we can use a lot of methods to find that root. That's we have the bisection method, we have the method of successive approximation, we have the first position method, the Newton's iteration method, and Ann's method, as well as the scanty method, among others. I have a video where we use the bisection method, the method of successive approximation, the fifth or the first position method. Please check it out on YouTube. Today, before the video ends, we'll look at the Newton iteration method, which people also refer to as Newton-Raphson method. So before the video ends, I will take you through what a Newton iteration method simply means. Then we'll take some sample complex polynomial functions and try to find that one real root. This will be a very interesting engagement, so please come along. So the Newton's iteration or the Newton-Raphson method simply says that if we have a function that is a complex polynomial function and a root exists between the interval a, b close. Remember, we get those intervals using the location theory, where b is greater than a. Then that one root can be found as xn is equal to x minus the function f of x over f prime of x. And what is f prime of x? F prime of x is just the differential of the function f of x. Remember that. And how do we get the values of x to substitute? So Newton is saying that our x naught will be equal to the halving of these intervals. That's a plus b all over 2. As we get x naught, our x1 will be equal to x naught minus f of x naught over f prime of x naught. Then when we get our x1, then our x2 will be equal to x1 minus, that we substitute x1 in place of x. So x1 minus bracket x f of x1 over f prime of x1. Our x3 will be equal to x2 minus f of x2 over f prime of x2. We'll continue like that until we have x of n plus 1 will be equal to xn minus f of n minus over f prime of n. So that's all about the Newton's iteration method. It's a little bit similar to the method of successive approximation. And one advantage of this is that the method of convection, or we can easily get the root easily. And another importance or advantage of this method is that there is no need to find which of the interval it will replace. It's just a matter of getting your correct previous x, then you substitute into the Newton's iteration formula to get your current approximation. This is very simple. So we take some sample questions and see how we can put this into practice. So we solve our first example. They solve x cubed plus 2x squared plus 10x minus 20 equal to 0 using Newton-Raphson method correct to 4 decimal places up to the third iteration. So this question, when we read the third iteration, we stop and we approximate that correctly to 4 decimal places. That is all what this is about. So we let our f of x to be equal to our x cubed plus 2x squared plus 10x minus 20. Now we find f prime of x. That means we differentiate this function. We'll get 3x squared plus 4x then plus 10. Remember, Newton is saying that our xn will be equal to x minus f of x over f prime of x. So we substitute to get the iteration formula. So what is our s? Okay, we have s. Our f of s is s squared plus 2s squared plus 10x minus 20 over f prime of s, which is 3s squared plus 4s plus 10. We need to write this very well. You know, remember this is over 1. So our LCM is this. So we have the LCM as 3s squared plus 4x plus 10. If this goes here, 1 divided by this will be this. This will multiply that. So we have x bracket 3x squared plus 4x plus 10 minus our s squared plus 2s squared plus 10x minus 20. So what we can let this multiply this. We have 3s squared plus 4s squared plus 10x. Then this will be minus s squared minus 2s squared minus 10x, then plus 20 all over our 3x squared plus 4x plus 10. So look at this. 3s squared minus s squared will give us 2s squared. 4s squared minus 2s squared will give us 2s squared. Then 10x minus 10x, that will be 0. Then we'll have our plus 20 divided by that. So when we simplify, we'll get this, as I said. Now we need to get the interval using the location theory. Remember, our f of x is equal to s squared plus 2s squared plus 10x minus 20. When we find f of 1, we'll get negative 7. And when we find f of 2, we'll get 16. Since this is negative and this is positive, it means a root exists within the interval 1, 2, close. Now how do we find our x0? Remember, Newton said x0 will be equal to the half. That's 1 plus 2 divided by 2. 1 plus 2 is 3 divided by 2. 3 divided by 2 is 1.5. So what do? We substitute this 1.5 into this to get our x1. So we can say our x1 is equal to 2 brackets 1.5 cube plus 2 times 1.5 square plus 20 all over 3 times 1.5 square plus 4 times 1.5 then plus 10. I hope you get that. Now we just simplify this, then we continue from there. So when we simplify this, 1.5 cube will give us 3.375, 1.5 square will give us 2.25, then plus our 20. Then 1.5 square, remember, will be 2.25 again, then in that order. Now to multiply this, we'll get 6.75. 2 multiply our 2.25, we'll get 4.5, then plus 20. Then when 3 multiply 2.25, we'll get 6.75. Then 4 multiply 1.5, we'll get 6, then plus 20. That's what we have there. So when we add 6.75 to 4.5 to 20 and plus 20, we get 31.25. Then 6.75 plus 6 plus 10, you get 22.75. When 31.25 is divided by 22.75, we'll get 1.3736. So that's our first iteration. Now remember, our xn again is equal to 2s squared plus 2s squared plus 20 all over 3x squared plus 4x then plus 10. Then we can find our second approximation. And how do we get a second approximation? We substitute the first x1 now into our iterative formula to get our second approximation. So this will be 2 brackets 1.3736 cube plus 2 bracket 1.3736 square plus 20 all over 3 bracket 1.3736 square, then plus 4 bracket 1.3736, then plus 10. So when we simplify that, that's 1.3736 cube will give us 2.5916, and 1.3736 square will give us 1.8868, then plus our 20. This one, to remember, this will give us 1.8868, then 4 times that, then plus 10. When 2 multiply this, we get 5.1832. 2 times 1.8868 will be 3.7736. Then plus 20. 3 multiply this will be 5.6604. Then plus 4 multiply this will be 5.4944. Then plus 10. When we add 5.1832 to 3.7736 to 20, we get 28.9568. And when we add 5.6604 to 5.4944, then to 10, we'll get 21.1548. When this divide that, we'll get 1.3688 as our second approximation. Now remember, the question says up to the third iteration. So now we substitute our x2 into our iterative formula. Remember, this is the iterative formula. We substitute our x2 into it to get our third iteration. So our third iteration, which is x3, will be equal to the substitution of the x2 into the iterative formula. So we'll get 2 bracket 1.3688 cube plus 2 bracket 1.3688 square, then plus 20 all over 3 bracket 1.3688 square plus 4 times 1.3688, then plus 10. When we simplify this, so 1.3688 cube will give us 2.5646, and 1.3688 square will give us 1.8736, then plus our 20. Remember, 1.3688 square will give us 1.8736 again, then plus our 4 times that, then plus 10. When 2 multiply 2.5646, we get 5.1292. When 2 multiply 1.8736, we get 3.7472. Then plus 20. 3 multiply that, we get 5.6208. 4 multiply 1.3688, we get 5.4752. Then plus 10. When we add, we have 5.1292 plus 3.7472. Then plus 20 will give us 28.8764. Then 5.6208 plus 5.4752 plus 10 will give us 21.096. When 28.876 is divided by 21.096, we get 1.3688 as our root. Remember, they say up to the third iteration. So we reach here, we stop, we obey the question by approximating it to 4 decimal places. Then we can say a root of the polynomial x cubed plus 2x squared plus 10x minus 20 equal to 0 is 1.3688. I hope you get that. We'll solve another example on this so that you'll be abreast with the concept. So our second example says that we should find one value of x if x squared minus 5 equal to 0 using Newton's iteration formula. So how do we do this? So we let our function f of x to be equal to x squared minus 5. What next? We find f prime of x. We differentiate this function with respect to x, we get 2x. So we get a Newton's iterative formula for this our polynomial function. So our xn is equal to x minus f of x over f prime of x. So this will be x minus our f of x, remember, is x squared minus 5. Our f prime of x is 2x. Remember, this is over 1, so the LCM is 2x. This goes here 1. This goes here 2x. We multiply x, we get 2x. Then minus x squared minus 5. So, when we simplify further, x times 2x will give us 2x squared minus x squared, then plus 5 all over 2x. 2x squared minus x squared, that will be x squared plus 5 all over 2x. So we can say that our xn is equal to x squared plus 5 all over 2x. So having gotten our Newton iterative formula for our polynomial function x squared minus 5 equal to 0, the next thing is we should get the interval at which the root exists using the location theory. So we can say if you find f of 2, that means when you substitute 2 here, 2 squared 4 minus 5 will give us negative 1. Then when we find f of 3, 3 squared is 9, 9 minus 5, that will give us 4. So since this produces a negative and this produces a positive, it means at least a root exists within the interval 2, 3 close. So how do we get that interval? Newton is saying that you have to get the starting value of x by finding the average of this. That's 2 plus 3 all over 2. 2 plus 3, that will give us 5. 5 divided by 2 will give us 2.5. What next? We substitute 2.5 as x0 into the Newton's iterative formula to get our x1. So remember our x0 is our xn is equal to x squared plus 5 all over 2x. Then our x1 will be equal to 2.5 squared plus 5 all over 2 times 2.5. So 2.5 squared will give us 6.25 plus our 5. Then 2 times 2.5 will be 5. Then when we add 6.25 to 5, we'll get 11.25 divided by 5. We'll get our x1 to be 2.25. Having got our x1 to be 2.25, we substitute the x1 into our Newton's iterative formula to get our x2. So we can say our x2 will be equal to 2.25 squared plus 5 all over 2 times 2.25. So our 2.25 squared will give us 5.0625. Then plus our 5, 2 times 2.25 will give us 4.5. On add 5 to 5.0625, we'll get 10.0625. Divided by 4.5, we'll get 2.2361. So, since we're not asked the number of times that we'll get, or the number of iterations we should do, we should find a third iteration. If it is the same as this, then we can stop. So, our third approximation will be substituting 2.2361 into our iterative formula. So, we'll get 2.2361 squared plus 5 all over 2 bracket 2.2361. So our 2.2361 squared will give us 5.001, then plus 5, then 2 times 2.361 will give us 4.4772. When we add 5 to 5.001, it's just 10.0001, then divided by 4.772 will give us 2.2361 as the same as it. That means when we continue substituting, we will still get the same value of that. Then we can say that our x, our positive root x, is equal to 2.2361. Look at it. Remember, we have x squared minus 5 equal to 0. That means x squared is equal to 5. When we find the square root of 5, you get that value. That's the 2.2361 as your answer. So this is all about the Newton-Raphson method. We saw one more example on this. So let's see our third example. They say find the positive root of x exponent 4 minus x equal to 10, correct to 3 decimal place, using Newton-Raphson method up to the third iteration. So remember we have x exponent 4 minus x is equal to 10. Please, you can pause the video and try solve. After that, you compare your answers. You have x exponent 4 minus x minus 10 equal to 0. And you can say our f of x is equal to s exponent 4 minus x minus 10. Then our f prime of x will be equal to 4s exponent 3 minus 1 when you differentiate that function. Then from that we can get Newton's algorithm to evaluate this as x minus f of x over f prime of x. And we substitute. Our f of x, remember, is s exponent 4 minus x minus 10 over f prime of x, which is 4x cubed minus 1. Now remember, this is the LCM. You can get our x of n as s bracket 4x cubed minus 1, then minus s exponent 4 minus s minus 10 all over 4s cubed minus 1. Our xn will be equal to, when s multiply that, get 4s exponent 4 minus x. Then this will give us minus s exponent 4 plus x plus 10. Then over 4s cubed minus 1. Now look at this. 4s exponent 4 minus s exponent 4 will give us 3s exponent 4 minus s plus s is 0. Then we only have 3s exponent 4 plus 10 as a numerator and 4s cubed minus 1 as our denominator. So having gotten our algorithm to evaluate our polynomial function, we need to find the interval where at least one root may exist. So what do? We find f of 1. Remember, our f of s actually is equal to s exponent 4 minus x minus 10. So I will find f of 1. Our f of 1 will produce negative 10, and our f of 2 will produce, our f of 2 will produce 4. So since this is negative and this is positive, it means a root exists within the interval 1, 2. Now we can find our x0. Our x0 will be equal to 1 plus 2 divided by 2. 1 plus 2, 3 divided by 2 will be 1.5. So we get our x1 by substituting our x0 there. So our x1 will be equal to 3 bracket 1.5 exponent 4 plus 10 over 4 bracket 1.5 exponent 3 minus 1. So when we evaluate 1.5 exponent 4, we'll get 5.0625, then plus our 10. 1.5 exponent 3 will give us 3.75, then minus 1. When 3 multiply 5.0625, we'll get 15.1875, then plus 10. Then when 4 multiply 3.75, we'll get 13.5, then minus 1. When we add 10 to 15.1875, we'll get 25.1875. Then 13.5 minus 1 will be 12.5. When we divide 25.875 by 12.5, we'll get 2.015. So that becomes our x1. How do we get x2? We substitute x1 into our algorithm to get x2. So we can say our x2 will be equal to, substitute that into our algorithm, so 3 bracket 2.015 exponent 4 plus 10 over 3 bracket 2.015 exponent 3 minus 1. You can say our x2, we simplify that, then we get our outcome. So this exponent 4 will give us 12.3359, then plus 10. Then 2.015 exponent 3 will give us 8.1814, then minus our 1. When 3 multiply 12.3359, we'll get 49.4562, then plus 10. Then when 4 multiply 8.1814, we'll get 32.7256 minus 1. 10 plus 49.4562 will give us 59.4562. Then when we subtract 1 from 32.7256, we get 31.7256. When this divide that, we get 1.8741 as our second iteration. Now we found our third one by substituting our x2 into our algorithms. So we find our third and final iteration according to the equation. Our x3 will be equal to the substitution of x2 into our algorithm. So 3 bracket 1.8741 plus 1 over 4 bracket 1.8, that's this exponent 4, then 1.8741 exponent 3 minus 1. Please, this is plus 10 actually. So this is plus 10. So now we evaluate this, then we take it from there. So 1.8741 exponent 4 will give us 12.3359, then plus our 10. Then 1.8741 exponent 3 will give us 6.5823, then minus our 1. When 3 multiply 12.3359, we get 37.0077, then plus 10. When 4 multiply 6.5823, we get 26.3292, then minus 1. 10 plus that will give us 47.0077. Then 26.3292 minus 1 will give us 25.3292. So on 25.3292 divided 47.0077, we get 1.8559. So since the equation is correct to 3 decimal places, we can say a positive root of, what is it, x exponent 4 minus s equal to 10 is 1.856. Correct to 3 decimal places. I hope you get that. We'll solve one last application to this. So we want to solve our last question. Before we do that, please remember to subscribe to my YouTube channel if you are here to. If you are new to this channel, like, comment, and share my videos. This will make my YouTube channel grow more, and I can record more mathematical content for you. Bigo, I know that you will do that. So now the question says, derive a Newton's algorithm for finding the square root of n. Hence, find the square root of 12. So how do we do that? Remember, we need to develop the algorithm to do that. We need to find a function. Then we'll find a Newton's algorithm. After that, we'll use the algorithm to find the square root of 12. So what do? We say we'll let x to be equal to the square root of n. So what do? Now we can square both sides. So when we square both sides, we get x squared is equal to n. Then we can say x squared minus n is equal to 0, where n is always constant. So our function f of x is equal to x squared minus n. Then we can find f prime of x. We differentiate this function. Remember, n is constant. When we differentiate this function, we get 2x. Now remember, Newton-Raphson is saying that a root exists. That root is equal to xn is equal to x minus f of x over f prime of x. So we have x minus, what's our f of s? F of s is x squared minus n, then over f prime of x is 2x. I'll simplify this further. This will be x bracket 2x minus x squared minus n all over 2x. I'll solve that further. S times s, 2x will give us 2x squared, and this will be minus s squared, then plus n all over 2x. 2x squared minus s squared will be s squared, and plus n all over 2x. Then we can say this will be the Newton's algorithm for evaluating or finding the square root of n. I hope you get that. We can still simplify this further by factoring 1 over 2. So we can still write this as half bracket x squared plus n all over x is the same thing. So this will be the Newton's algorithm for simplifying the square root of n. Now the question is, having known that, we should find the square root of 12. So we want to find the square root of 12. Before we get that, we need to get the interval. How do we get the interval? We find all perfect squares down. So remember, perfect squares are 1, 4, 9, 16, 25 in that order. Now, 12 will exist between 9 and 16. You get that? So we can say that the square root of 12 will exist between the square root of 9 and the square root of 16. That interval. What is the square root of 9? The square root of 9 is 3. And the square root of 16 is 4. That means the root or the square root of 12 exists between 3 and 4. I hope you get that. So now, remember Newton's iteration is saying that our x naught will be equal to the halving of that interval. So our x naught will be 3 plus 4 all over 2. 3 plus 4 is 7. 7 divided by 2 will be 3.5. So now we substitute 3.5 into our algorithm to get our x1 and we'll continue from there. So remember, we got our algorithm to be x squared plus n all over 2x and our x0 to be 3.5. What is this n? The n is this. So we are evaluating the square root of 12. So n is 12. So our n is equal to 12. So our xn will be equal to x squared plus 12 all over 2x. Then we can find the first iteration, x1 to be equal to 3.5 squared plus 12 over 2 times 3.5. So our 3.5 squared will give us 12.25 plus 12. 2 times 3.5 will be 7. 12.25 plus 12 will be 24.25. When we divide that by 7, we'll get our x1 to be 3.4643. We find the second algorithm to see. So our x2 will be substituting our x1 into our algorithm. So we have 3.4643 squared, then plus 12 all over 2 bracket 3.4643. So our x2 will be equal to, so 3.4643 squared will give us 12.0014, then plus our 12. 2 times 3.4643 will give us 6.9286. When we add 12 to that, we're getting 4.0014 over the 6.9286. When 6.9286 divided between 4.0014, we'll get 3.464. Then we can say the square root of 12 is actually equal to 3.4641. You can take your calculator, point the square root of 12, you get 3.4641, correct to 4 decimal places. We'll end it here today. Please remember to subscribe to my YouTube channel. Check out my videos on how to find at least one root for complex polynomial using the other methods on YouTube. Until we meet again, my name is Tete J. Richard.